You can see here in video number 16 that we're doing question number 23, and once again we're solving for a conditional probability using Bayes' theorem. This time the information is given to us in a table, tabular form, which makes it kind of nice actually. I've been advocating using tree diagrams to help you solve Bayes' theorem problems as quick as possible, but this time with a table, it's kind of like the table acts as your tree diagram. You don't actually have to draw one. It makes the problem actually a little simpler to think about, I think. So the problem says an actuary studied the likelihood that different types of drivers would be involved in at least one collision during any 1 year period. The results of the study are what is shown in the table. See, first of all, you've got the type of driver, teen, young adult, midlife, senior. They don't give the age ranges, but you might guess that teen would be 16 to 19, say. Young adult would be 20 to 39, perhaps. Midlife would be 40 through 64, and senior would be 65 and above. You've got these percentages here, which you can think of as probabilities. So this 8% would be the probability that a randomly chosen driver is a teen. The 16% would be the probability that the randomly chosen driver is a young adult. 45% the probability that a randomly chosen driver is in midlife. And 31% would be the probability that a randomly chosen driver is a senior. Okay? So you can go ahead and label those right away. And that's another benefit of the table. You can just write these things down in the table itself. Next, you need to realize that these numbers represent really conditional probabilities. This 0.15 is the probability of greater than or equal to 1 collision. This is the way it says it on the table, but that is based on the fact that you're in this row, that you know it's a teenager. That's the given information. So this is really a conditional probability. The conditional probability of C, say, which represents greater than or equal to 1 collision, given that the driver is a teenager. 8% is the conditional probability of collision given that the driver is a young adult. The 4% is the probability of at least one collision given that the person is midlife. And finally, the 5% is the probability of C given S. S represents senior here, not the sample space. Okay, so this is a big hint that this is going to involve Bayes' theorem. You've got these categories which really represents a partition of the sample space. These are non-overlapping, and their union is the entire sample space, representing every driver being in exactly one of those categories. And you know conditional probabilities, and you want to find a conditional probability as well. Given that, that's a big hint. Look for those kind of words. Given that a driver has been involved in at least one collision in the past year, calculate the probability, even though you don't see the word conditional probability in there, that is going to be conditional, that the driver is a young adult. Okay? Notationally, we're trying to find the probability of Y given C. Okay, you always put the given thing after the vertical line. That is different than this. Okay, they're not the same thing. That's really important to realize. Okay, and we will use Bayes' theorem, but I will solve the problem as quick as possible, essentially by extending this table over here to the right and then doing a calculation. I will then draw a Venn diagram to illustrate the solution intuitively. And then at the end, at the bottom of the sheet, I actually have a formal statement of Bayes' theorem that I'll show you, and we'll compare with what we did. Okay? So as with the tree diagram, where you multiply the numbers along the branches, here you're going to multiply the numbers along the rows. For example, I take 0.08 times 0.15, I get 0.012, and that number, 0.012, by the general multiplication rule, would be the probability of C and T. A randomly chosen driver has a 1.2% chance of both having at least one collision in the last year and being a teenager. The product across the next row, 0.16 times 0.08, is 0.0128. By the general multiplication rule, that is the probability of C and Y. Okay, these are unconditional probabilities. We're not assuming anything that is known ahead of time in writing these probabilities here. 0.45 times 0.04, 0.018, that would be the probability of C and M. Intersection symbol again means and. And finally 0.31 times 0.05, 0.0155 is the probability of C and S. Okay? Now, to solve the problem, and again, I hope this is pretty intuitive for you, to find that conditional probability, it's going to be the ratio of the product here corresponding to y and c. So that's going to be this one right there, 0.0128, divided by the sum of these probabilities. The sum of the probabilities really represents the chances of C occurring. Okay, the sum would be 0.012 plus 0.0128 plus 0.018 plus 0.0155. So we get 0.0128 divided by 0.012 plus 0.0128 plus 0.018 plus 0.0155 is 0.0583. Do that ratio. I'm going to, on this old kind of calculator, I'm going to take its reciprocal here first and multiply times 0.0128. And you get about 0.21955 approximated to 0.22, and that is answer D on the sample exam questions, and that is the correct answer. Okay, about a 22% chance. You can see Bayes' theorem statement down here. We'll come to that here. But before we do that, let's make a Venn diagram and think about why this makes sense intuitively. So this represents the sample space, all the drivers. Again, these four events form a partition of the sample space. These are disjoint sets whose union is the entire sample space, and we can, for intuition's sake, make the areas of these things the actual percentages that you see here. If you imagine this rectangle having an area of 1, the teen would have an area of 0.08, maybe about like this or so. That would represent teenagers. The young adults would be 0.16 area, double this area, so double the width, maybe about like this. The midlife is 45%, the senior is 31%, maybe something, well, this is not a perfect drawing, maybe something about like this. I should probably make this one a little smaller here. Let's make this midlife and this senior right there. Okay, so that's the partition of the sample space. And then you've got being in a collision overall. Now the sum of these is the overall probability of being in a collision, which is 0.0583, which would be the area of the green region I'm about to draw representing C. But these conditional probabilities are the relative areas. So for example, this 15% is the relative area of the collision in the T rectangle. 15% of T's area is given by C. Likewise, 8% of Y's area is given by C, maybe about like this. 4% of M's area, about like this. And finally, 5% of S's area, about like this. All four of these form C, the event that there's at least one collision during the year. And you can see these are disjoint, and essentially in finding this denominator here again, we added these numbers. These represented, again, this partition of C here in this case, and we really used the special addition rule for disjoint events there. The probability that we wanted to find, the conditional probability, is the conditional probability of Y given C. So C's occurs, it's like you've shrunk the sample space to just being these green rectangles combined. What percentage of the area of those rectangles is made up by Y? What percentage of this area relative to the entire area of C? That will be the answer, and it's about 22%, and that should seem reasonable looking at the picture. All right, now let's look at the statement of Bayes' theorem to finish off the video, and we'll compare it with what we did. So here's the formal statement. Suppose a sample space, S, it's not the same as this S, is the union of a bunch of sets whose intersections are empty. These are disjoint sets, non-overlapping, mutually exclusive events. Suppose further that the probability of each of those events is greater than 0, just like these numbers are all greater than 0. These are the B's, okay, in Bayes' theorem. And these probabilities are all greater than 0. For any event A is going to be represented by C here, whose probability is greater than 0. And for any J between 1 and n, the probability of Bj given A is this ratio, which can ultimately be written as this ratio. And this ratio is what we calculated here. Now you don't see the products in this fraction here that you see down here. However, we already did the products up here. These numbers up here that we figured out were products across these rows. Those are the products that you see both in the numerator here and the denominator. So comparing with what we did here, bj really is y, a is c, and the other b's, b, b1, b3, and b4, say, are t, m, and s. Okay? So you can see how this matches with Bayes' theorem, but we don't have to use the formal statement of the theorem to solve the problem. We can solve the problem more quickly in another way.